going to go ahead and kick off because we've got a lot of great content to get through today. Firstly, I'd like to acknowledge the traditional custodians of the land, and in my case here in Sydney, that is the Gadigal people of the Eora Nation, and pay my respects to the elders past, present and emerging. Thanks everyone for joining. My name is Belinda McEwen. I'm Developer Marketing Manager for Australia and New Zealand, and I'm very excited to be joined today by Chris Coombs, Solutions Architect here at AWS. Thanks for joining, Chris. Chris will be taking us through how you can improve your existing applications with serverless principles for the next 40 minutes. We'll then have a 5-minute break before jumping into your choice of 2 follow-along workshops: the right tools to build event-driven applications on AWS, or an introduction into service coordination using AWS step functions. If you have any questions for Chris, just pop them into the questions panel to the right, and if there's time, we'll answer them at the end. And if there's any questions unanswered, we'll follow up with you by email in the coming days. Lastly, just in terms of housekeeping, at the end of the session, there's a quick 3-question survey to help us understand whether you enjoyed the session and what you'd like to see more of. We'd really appreciate your responses to those questions. Without further ado, I'm going to hand over to you, Chris.
Awesome, thanks very much. So, hello everyone, and thank you for tuning into today's webinar. I am Chris Coombs, a Solutions Architect based out of Melbourne, Victoria. I myself am an avid builder and part of the serverless field team here at AWS. There we go. And today we're going to explore how you can improve your existing applications with serverless principles. I'm going to cover how you can inject new functionality into your existing application and reduce code complexity with serverless. I'll walk you through augmenting an existing traditional server full application with serverless events, orchestration, and integrations. I'm going to demonstrate how to ingest objects and data to trigger events, to remove orchestration complexity from your code and integrate natively with AWS and third-party services. And we're going to do this today based on patterns that have been tried and tested with customers in the field. And I look forward to sharing not only the aggregate successes, but also to share with you some of the anti-patterns to watch out for as you go along this journey. Now, I've mentioned serverless quite a few times already, but what is it? Well, for people that know me, I use serverless as a synonym for AWS Lambda, but it's much, much more than that. It's a term which encompasses not just services, but also practices and strategies that enable you to innovate and respond to change faster, or as I like to say, to build better. Now, with serverless technology, management tasks like patching and capacity provisioning are a thing of the past. For example, services like Lambda come with built-in high availability, automatic scaling, and my personal favorite, a pay-for-use billing model. Lambda, which again is our serverless compute platform, is now billed by the millisecond. Ultimately, serverless means that we as builders have to write less boilerplate code, maintain fewer pieces of technology, and just focus on making our products better. And if that all sounds great to you, that's good because, well, it is. But as much as I do love serverless, and I am a serverless fanatic, it shouldn't be the end goal in itself. As developers, engineers, as builders, our job is to solve business problems. And while serverless can certainly aid in this, we shouldn't lose sight of why we're running that serverless technology in the first place. Now, those business goals can be varied. Like, they could be providing more scale to improve the user experience at peak times. It could be reducing the time to market for a feature or bug fix. Perhaps we want to provide more third-party integration options for customers. Whatever the goal is, we need to keep that as our North Star and pick the patterns and technology to best deliver those results. I'm certainly hoping that by the end of this talk, I'll have persuaded you that the patterns we're going to look at are the right ones and that serverless technology is the best tool for the job in this instance. But it may not be the only tool. We certainly make trade-offs all the time in our daily work and personal lives. And it may be that spinning up a Lambda function is just a bridge too far for your organization at this time. And that's okay. You can still use the patterns we're going to talk about today with server full technology but unfortunately, you'll miss out on some of those amazing serverless benefits. So let me set the scene for today. We have an existing application. Now, some people might call this a monolith or a legacy app, but given the negative connotations folks tend to ascribe to those words, let's just call it the app. Now, it's been serving us well for many, many years. We're using managed services now to reduce our management efforts. We have a pretty good idea of where one piece of functionality ends within the code base and another begins. And when all is said and done, it's not on fire. It could certainly use some love, but it works. That being said, we do keep getting complaints from the business that when we deploy changes to one piece of functionality, sometimes new or even worse, old bugs pop up in another piece of functionality somewhere else. We found that it's hard to scale components independently when there is particular demand for something like new signups, which we think is largely due to our shared database model. And due to the age of the application, it's hard to find good development talent in the market, which is leading to engineer burnout, that's making it harder to get those new features developed. And look, this is obviously fictional, our application here, but that's a pretty common story that we hear. And typically we can map these types of problems back to one or a combination of the following things. A tightly coupled application where everything is deployed together, typically as a unit, where scaling individual components of the application is non-trivial, again, usually to this shared data store, having a large impact or risk of change, it being difficult to adopt new features or technologies due to dependencies with other application components, long deployment processes, and long testing cycles, if and where it exists, and it being difficult to iterate and extend the application quickly. Now, having worked with customers to modernize their applications, there is a specific overarching pattern which has been very successful in overcoming these challenges, namely, I think you guessed it, microservices. And as I'm sure you all know, microservices are minimal services that are designed around business capabilities, and they're deployed separately but can interact together to achieve a broader use case. And now, crucially, each microservice should have its own data store, but it can be implemented in any technology you choose. Interactions with the microservice are through well-defined interfaces, such as REST APIs or event messages. And whilst we'll explore some of the microservice design and implementation patterns now, if you would like to dig deeper into the concept of microservices and bounded context and things like that, I certainly recommend joining Tomas's workshop on event-driven applications, which is right up next after this webinar. So microservices certainly sound like they will solve all of our problems that we listed before that our fictional business raised with us. But in practice, we don't tend to completely rewrite an existing application into microservices, certainly at least not in one go. As with modern development practices, which teach us to iterate frequently and learn from feedback, you want to take the same approach with your microservices. I suggest starting with one business problem to solve, which might result in one or two new microservices, and use that as an opportunity to iterate on your build, test, and release processes. Use it as an opportunity to learn as an organization how to look after these microservices, to monitor them, report on them, and that sort of thing. The idea of adding new functionality or extracting existing functionality from the app into new microservices is probably best known as the Strangler Fig pattern, which I only recently learned actually grows in Queensland. The idea being that the plant these new microservices will wrap around, the application will wrap around, the microservices will wrap around the app, which forms our core structure. And over time, we keep adding more and more microservices, much like the plant does. It wraps around the tree. But here I think the analogy may go too far. The Strangler Fig eventually kills off the host tree it wraps around, but that may not be necessary for you and your app. If we can solve our business problems with one or two microservices, then there's no reason to kill off the core app. At risk of laboring the point, the goal isn't to microservice all the things, or even to serverless all the things, although that does sound great. It's to meet business objectives. And if that can be done with a handful of microservices, then that's all you need. Okay, so enough of the theory, time to get practical. How do we get the existing application and new microservices to run alongside each other? How do we get that fig plant to wrap around the tree? Well, this actually leads me to another pattern, which has been hugely successful with customers, which is the proxy pattern. Unimaginatively, the goal of the proxy pattern is to put a proxy between your app's consumers and your app so that we can shift traffic from the app to the new microservice piece by piece, and crucially, without modifying any application code whatsoever. So when we're doing this, we always want to make sure that our app happily coexists with the new proxy first. So the first step is to simply add the proxy layer and to forward all the requests to the existing application. We'll then keep an eye on our app metrics and customer support calls. If all goes well, we can move on to adding our fig plant. So in our example, the existing app has an invoices module, and we've extracted that module out into its own microservice with its own database, and it has its own interface. It's now time to update our routes in the proxy to switch requests from the app to our microservice. And then typically, over time, you will add more and more microservices, switch over more routes, and for the new microservices, create new routes. If you already have a routing layer, then you could just add this logic there. AppSync, our serverless GraphQL service, for example, has this concept baked straight into it. So it should just be a case of updating the relevant resolvers. But if you're creating a REST-based routing layer from scratch, I certainly would recommend using another one of our services, API Gateway. So with API Gateway, which is our serverless API Gateway service, we can target our existing application in its VPC, and then add our microservices by creating routes and adding each of our new microservices as integration targets. So let's have a look for a second. We have our app living on EC2. Which lives behind application load balancer, or an ALB. And what I've done is I've created a load balancer, which is because I'm using the REST version of API Gateway. And API Gateway will use that network load balancer to be able to access resources inside of your VPC. And thanks to a recent feature release, I'm now able to target the application load balancer directly from the network load balancer, meaning that I don't need to change my networking topology at all. I don't need to shortcut anything. I can leave it exactly as it was, and I can just point to it. This we call, this registering API Gateway with that load balancer, we call VPC link. All right, so next we're going to go ahead and create a proxy resource, which is a special type of resource in API Gateway that's going to take all requests, and as you can see here, it's going to send them through to the VPC proxy. And then we're going to create a new route, which in AWS and the API Gateway speak is a new method and resource. And this is going to send those requests to an SNS topic, which is our serverless notification offering. And the reason why I'm doing that and I'm not just calling /invoices, so that I'm letting the application know that someone has placed a new order, but then we've decoupled our invoices microservice so that it can go ahead and pick up that event and process it if it wants to. This means, for example, that if the invoices microservice is down for whatever reason, the order is still placed and other microservices might pick up the order to do their thing, for example, allocating stock, but then the failed invoices eventually can be replayed from the topics.ledger queue when invoices does come back on later online. And we'll talk more about this later on. But I just wanted to show you that what that implementation looks like in practice. And I really do recommend using REST API Gateway as your proxy, as it's packed full of features like message validation, built-in authentication mechanisms, API keys, and usage plans, to list just a few. But I think that probably warrants a whole talk in itself. So Ultimately, I think using something like REST API Gateway, you can remove that boilerplate code from your app, giving you less to think about, less to reason about, less to maintain, and hopefully better performance. I mean, I think the authentication caching you can get with API Gateway is worth the price of admission alone, but I said that's probably for another talk. And of course, API Gateway isn't the only way to build a proxy layer inside of AWS. For example, if you don't need all of those features and then you just want to be able to route traffic, an application load balancer target groups could work just fine. And if you need static IPs for whatever reason, you can add the network load balancer on top, just like we did with the VPC link construct. So just to give you an example of this, I can set up the same rule for sending requests to /orders, but to a different target. In this case, there isn't the same array of options for application load balancer targets, but in a pinch, I could use a Lambda function to push that event to SNS. And once I've created the target group with that inside, I can then set up a rule that uses the orders path to send that request to the target group, which will then send it to Lambda, which will send it to SNS. So look, application load balancers do support OIDC compliant identity providers. So there's an option to extract some of that auth code from your app still. So there is some overlap with API Gateway there. Now, if you're confused as to which tool in the kit bag is right for your app, please don't hesitate to reach out to your AWS account team for advice. We can have a look at your specific requirements, business objectives, and we can advise on what the right technology might be for you. Now, the proxy pattern works really well for microservices which are triggered by consumers of your app. But what about communication between application components? In our example here, rather than making a one-off purchase, someone has signed up for a subscription. And we'll still want to generate an invoice for that, but how do we best communicate the subscription to our new invoice microservice? Well, there is a pattern called the abstraction pattern, which is essentially amounts to modifying your application code to create a wrapper around the component you're looking to move out into its own microservice. We usually refer to the wrapper as an interface. When we first design and implement the interface, we usually leave it pointing at the existing code base for a while, again, to make sure we haven't inadvertently broken anything. But then it's across our microservice. Once the new microservice is deployed, the interface can be switched to target the new microservice rather than the now legacy code. If you're thinking that this looks similar to the proxy pattern, you'd be right. And I like to think of the interface as being a little per component proxy. However, I will add a word of caution to anyone thinking of using this pattern. You do have to watch out for walking unintentionally into an anti-pattern, that anti-pattern being the distributed monolith. You'll notice that the arrows in this diagram all flow in one direction. There's essentially a call chain baked into the code. And whilst we might be able to get some benefits from this architecture still, for example, the microservice might be written in a more performant language, use a more appropriate database technology, or whatever it might be, the microservice might still be tightly coupled. So depending on how we've engineered it, we might still end up having to deploy both the existing application and the microservice in tandem. And with that, we get the same heightened risk of change, longer deployment cycles and testing times, all those things we were trying to avoid in the first place. But if you think back to our API Gateway implementation of the proxy pattern, what we really want to be doing is emitting an event like we did to SNS, rather than building a call chain. So what are these events? Well, an event essentially broadcasts that something has happened inside your application. And then it's up to the other microservices whether or not they may be interested in that event, and they may or may not process it. So rather than use an abstraction, which does require code changes and can often lead to distributed monoliths when not used correctly, one pattern I've seen used with success on many occasions is the change data capture, or CDC pattern, whereby an event is emitted as a side effect of an insert, update, or delete in a database, and then microservices consume those events however they choose. Now, Despite the name, this pattern is not only useful with databases. Anything which can produce events when data is changed can potentially form triggers for your microservices. For example, our app also has an SFTP component. Third parties looking to sell their content on our site can upload their catalogs, and our app will load that data in for discovery by our app's users. And the app currently pulls all the data on a cron and loads them into the database, which the existing components all reference directly via database calls. In this instance, the SFTP server we're using is backed by Amazon S3, so we can configure event notifications. So when we emit events in response to catalog, the catalog being added, updated, or deleted, we can actually then trigger, as you can see here, Lambda, SNS, or SQS. We're going to trigger a Lambda function. And we're going to do that because the Lambda function can pull the object, it can run a simple diff, and then emit each of the change records as an event via something SNS, or in this case, we're going to use EventBridge. As in our example, the catalog microservice will still store most of the data, but the invoices microservice only wants to listen for records which have had their prices updated. So we're going to apply some filtering, and we're going to create a rule against our EventBridge event bus and supply a custom pattern here, which in this case matches if one of the diffed fields is price. Now, with traditional databases, there are many ways to perform change data capture. For example, with database migration service, you can replicate changes directly to Kinesis, or you could target S3 and use the same S3 notifications pattern I just demonstrated to generate events. Or maybe even use native solutions like the Write-Ahead or Binlog. For some services, CDC is baked in as part of the product. DynamoDB, for example, which is our serverless NoSQL database and my personal favorite, has a feature called DynamoDB Streams, which emits changes to items in the database to a DynamoDB stream, or a Kinesis stream if that's more your thing. But the result is the same. Database events are emitted, and then it's up to the microservices whether or not they choose to consume them. Now, depending on how the database is modeled, the event which is emitted could contain all of the information needed to construct a meaningful business event, or it could just be a limited subset of data which exposes the internal design of the source database, which it isn't ideal. So one way to augment your database events is to trigger something like Lambda before the event is emitted to an event bus or similar, and add additional data to the event. But this kind of feels like doubling up on our work. If we're going to modify the code, couldn't we just generate the complete business event from inside our app in the first place? And if we think back to the abstraction pattern, we have a great place to generate these events in the interface. So we can essentially swap out the interface for an event generator. Again, this does require us to modify the app's code again, and the resulting architecture is a little confusing as we now have the invoices component essentially creating a subscriptions event in this example. As such, I'd simply recommend bypassing the old invoices code altogether and generating the business events directly in the subscriptions component instead. So kind of final thoughts on the abstraction pattern are that it can be useful as a stepping stone on the way to microservices, but I'd certainly recommend time boxing the implementation of it, ensuring that the interfaces are eventually removed and replaced with upstream event emitters. So with this new model, we're essentially changing the way we look at our application from one where components issue commands to an architecture where components send out notifications. And this we call the choreography or event-driven pattern. Now, the key thing to understand about the choreography pattern or event-driven pattern is that when a component emits an event, there's no expectation that another component or microservice will actually pick up that event. It's completely up to the subscriber. Now, this usually works well between bounded contexts, but there will be occasions where synchronous responses are required. For this, the microservice usually exposes a well-defined contract like a REST API and will likely have some orchestration logic which sits on top. Now, this orchestration logic is likely a microservice in itself, and I'd kind of recommend putting it in a microservice itself. But my advice would be that in these cases, the microservices should still emit events, even when returning synchronous responses. Because with this hybrid pattern, the application is able to respond synchronously, but also provides the flexibility and loose coupling we need for other features to be built alongside our app, which allows the possibility for our fig plant to continue growing. Now, again, to get practical for a second, there are many different ways in which to consume events on AWS. A popular model is publish and subscribe, or PubSub, and SNS, our SNS service is a great choice for publish and subscribe, particularly when you want to send an event to many subscribers, which we call fan out. With this pattern, a microservice can subscribe to a topic and then be pushed events as they are sent to the topic. Or with something like Kinesis, events can be pulled, or this might be referred to as polling. You might already know this kind of pattern if you're familiar with something like SQS, which is our queue service. Now, our serverless queue offering is a fantastic solution for queue-based systems with a single logical consumer, but with microservices, we're assuming there may be many consuming microservices. As such, something like Kinesis can be more useful when pushing events between bounded contexts. One thing to look out for with Kinesis, though, is the maximum number of subscribers to a stream. A centralized stream does provide the ability to perform near real-time data analytics across all of your events, which may be very useful if that's a use case that you have. You may need to dedicate at least one of those consumers to replaying events to a fan-out service like, again, SNS, depending on the number of microservices that you're expecting to have. Like I said, there are many different technologies to pick from for routing your events, and it largely depends on your use case. So if you're wondering, again, which technology is for you, please do reach out to your AWS team for guidance. And again, we'll have a look at your requirements and help there. So EventBridge, for example, which is similar to SNS in many ways, allows you to filter on the message payload, not just on the attributes, message attributes like with SNS. So as in this example, the promotions microservice, we've decided it's not interested in subscription cancellations for now, as we only have logic for promoting things to new users. And so by creating a filter in EventBridge, the promotion service can be sure it will only be triggered for new subscriptions, not cancelled ones. EventBridge also supports the durable storage of events so that they can be replayed in future, which is important for some customers, has a schema registry, and perhaps most importantly of all, has a lot of great integration options. For example, a microservice might be composed of a step function state machine and can be triggered directly from EventBridge as one of its many target options. And you can see there's quite a few target options there. But for now, we're going to pick a step function state machine. Now, state machines like those found in our step function service are pretty much the antithesis to the choreography pattern. State machines strictly define the path that data will take through your system. The app in our example has lots of custom code which defines the workflow for our data, but it is expressed in terms of calls to external systems like APIs or databases, conditional statements, data manipulation, and error handling. It just looks like normal code. We call this pattern of defining the flow of data through our application orchestration. The orchestration pattern is most commonly adopted inside a domain or bounded context. And I'm positive that you'll find examples of orchestration throughout your code base. Typically, this code itself doesn't provide unique business value, but it is necessary to invoke the pieces of code which do have business value at the right time. So without configuring logging and observability, it can be difficult to see the many paths an invocation may take through an orchestrated system that's just written in code. Like, how does a request traverse the many if-else statements? Where did the request become stuck? How do we roll back? These problems can be addressed by extracting our orchestration code to a state machine service like step functions. But before we get into building state machines on AWS, again, I want to just put out a word of caution. Whilst most customers will use their orchestration pattern within their bounded contexts, it can be necessary to orchestrate interactions across bounded contexts. For example, where each microservice must perform a synchronous transaction which must succeed in order for the next one to be invoked. Now, with microservices where each microservice has its own data store, a failure in one microservice can't be rolled back as part of the same database transaction, as now each of the microservices has its own database. One way to handle these failures is to emit events and then for each microservice to roll back its own local transaction individually. But there may be occasions when you need to orchestrate this rollback, usually for the same reason you needed to orchestrate it in the first place. And this workflow diagram demonstrates something called the Saga pattern, which allows us to handle failures in each microservice's invocation and then roll back each of the local transactions in the preceding microservices. For example, if booking a hotel and flight is successful, but booking a car fails, the workflow rolls back the previous steps by calling the cancel operations in reverse. For example, in this common scenario, we're canceling the flight and then the hotel. But my word of caution is this: orchestration within a bounded context is useful and often a necessity. But as with the abstraction pattern, it's possible that outside of the bounded context, orchestrated microservices can unintentionally become distributed monoliths. My tip for keeping microservice orchestration loosely coupled is to keep the orchestration logic in its own microservice. It can be responsible for that orchestration. It may call the invoicing service and require a response, but it shouldn't be generating any invoices itself. Rather, this orchestration microservice is responsible only for the orchestration, not the implementation of those services. Moreover, whilst the Saga pattern can be helpful for rolling back failures, if the orchestrator can actually tolerate failure of one of the number of the microservices it calls, it makes the microservice itself way more reliable, which is again one of the benefits we're looking to gain from adopting these practices and serverless technology. This pattern can also help with the state where, for long-running processes, microservices have changed, and the orchestrator can ensure that the data is processed by the right version of each microservice. But within a bounded context, an externalized state machine is a great way to define your workflows. In AWS, I'd certainly recommend using step functions for this purpose. A step function state machine is described in JSON or YAML and captures the various paths your data can take through your system. You can call out to various integration points and perform data transformation. Now, I must admit, manually crafting a step function state machine in JSON wasn't all that fun. That was until the step functions team released the Workflow Studio. Now with the Workflow Studio, I don't need to worry about that JSON. I can run through code in an application, an IDE on one side, and drag and drop the widgets I need to emulate that behavior in a step function state machine on the other, which is what we're going to do here. So for example, we've got some pseudocode here, and what we're going to do is kind of work through it. And the first thing we've got is we're going to check whether or not the event type is a cancellation type. So we'll go and pick the choice block, the choice flow, and we'll add that there. And so we'll add this choice state. Next in our code, we have a promise, which is essentially a parallelization, which we can easily do in step functions. We can create a Lambda function for each of the functions inside this promise. And we're doing that because I'm assuming that this code does some kind of scoring or has some other smarts, which is why we'll leave them as Lambda functions for now, not direct database access. Then in our code, we have this indexing of a previous result. And if you're not familiar with JavaScript, it may not be immediately clear what's going on here. Essentially, I'm trying to access the result of the first function in the promise. And I've exposed it here, but typically this is actually hidden in a kind of a hidden call chain. Whereas with step functions, I can add this as part of my parallelized state. And it's really easy to see how it fits into the overall flow. So I've got that if statement there based on the recommendations, and then I can invoke this, I can go ahead and get any bundles we might have for courses we want to recommend to that user. So once complete, I can add our promotion calculation code. Again, this is code which is unique to our business and therefore belongs in its own little Lambda function. Then we want to save the results of this whole process to DynamoDB for audit purposes. So there's no need to spin up compute for this, as we can natively integrate with DynamoDB, in this case an update item call, direct from step functions. It's worth noting that we could also read from DynamoDB if we wanted to. The DynamoDB action suite is very, very useful. Then we have our final choice state. If we have promotions to send to the user, then we can send those. In this case, we're going to choose to do this ourselves through SNS. Of course, once I finish this, I'll need to go back through and actually configure the relevant choice rules, add a few new default states, and point each of these actions to a real AWS resource. But I hope that this shows the value in externalizing our data flows into a state machine. And if at some later point we want to swap out some of our code for a machine learning model, for example, it's as easy as picking the state machine, the SageMaker runtime invoke endpoint API in this case, and switching it out for that Lambda function. Copy paste error. All right. And let's assume we have a notification service. Rather than send our message directly to the user, we can call the notifications module in our app via the proxy API gateway we set up at the start. And in this case, as we want to command the notification service rather than emit an event, we interact synchronously with its API. Now, one thing I haven't done in this step function is emit an event. I could easily add another step at the end to publish an event to EventBridge, or I could potentially even use DynamoDB Stream's CDC capability to generate events based on the update item call. Whether it's running a process in parallel or invoking an AWS API, I can drag and drop, and the best bit is I can view the definition and export that again as JSON to CloudFormation or whatever your infrastructure's code tool of choice is, and then I can go ahead and delete all of that orchestration logic from my code base, which hopefully leaves behind only the business value generating code, which we've split out into Lambda functions and can call as part of this state machine. Now that was a really quick run over the new Workflow Builder, Workflow Studio. But if you're interested in giving step functions a go for yourself, working out how to do data manipulation, those rules, I recommend checking out Ian's session on service coordination with step functions straight after this webinar. All right, so today we looked at injecting new functionality into existing applications with microservices and the proxy and event pattern. I demonstrated augmenting an existing traditional server full application with serverless events like S3 notifications. And I demonstrated using choreography with SNS and EventBridge rather than the more traditional orchestration approach. I demonstrated how to ingest objects and data to trigger events with AWS Transfer Family's SFTP server and API gateway. I removed orchestration complexity from code and provided native integrations with AWS services by using step functions, state machines. But more than that, I hope that you take away that as builders, our goal is not to serverless all the things or just do microservices or even apply these patterns as great as they are. Our goal should always be to solve business problems through picking the right technology and patterns, which I would argue in this case just happens to be serverless. And also that you're not alone in your journey. Lots and lots of customers are going through this, so there's lots of shared learning. So please do reach out to your AWS team with any questions you may have along the way on your journey. So again, thank you for taking the time to join in today. If you would like to get your hands on with either event-driven architectures or state machines, please do have a look at these great workshop sessions, which start in a few minutes. All that leaves me to say is thanks again and go build.
Thanks. Thanks so much, Chris. For folks who are still on the line, you can use this QR code to join us at one of the upcoming workshops, and we'll see you there. Thanks.